last day of classes. But before I start, I want to really, really thank all of you for sending me those cards. I was truly touched. And the cake was absolutely wonderful. I would say it was as good as the one I made. So that's a big compliment.
She was just talking about how she was worried that yours would taste better and it wouldn't be as good.
Yeah, no, I would say as good as one, and that's a big compliment. Very, very, I appreciate it. But thank you very, very much. That was very touching. On chi-square and binomial, I got a feeling that those of you who sent me an email that you almost got everything, especially that I sent you the right answers, so to check to see. I have two things that I want to accomplish tonight. One, I want to talk about correlation. And that's a simple thing. It's almost one full chapter, and I have summarized everything in here. Everything you want to know and more would be in this one page. 30 pages, all in here. A very simple concept. No sane person will ever do it by hand. There are a lot of complications. Even if you do it by hand, still you're halfway through. I'll show you why that is the case. So to do it on the computer, it is just a matter of a couple of clicks. Probably one of the easiest things to do on SPSS would be correlation that I'm going to talk about. Then after that, I want to get to the real statistics. Everything that we have learned so far was really a elementary to put your foot into the door for regression. Everything we have learned was really basics to get to this point of regression. Think about it. We learn about t-test, for example. Is there a difference in the salary of men and women? No one will ever do that. Think about it. Obviously, your salary has to do with a lot of things. Gender would be one of the things. Salary is affected by your level of education, by your gender, by your race, by, I don't know, a lot of things. To say to get the salary and see whether average salary men and women are different would be a little bit too simplistic. ANOVA would be the same thing. It is a silly thing. Is there a difference in the salaries of black, white, and Hispanic? That's really a silly thing to do. You never do that because your salary has to do with your gender, your race, with your level of education, years of experience at work, bunch of other things, correct? But those are important things to know. The concepts are important to know. What you want to do is regression, which is you want to write an equation and put all of these things into that equation. I'll get to that. I want to show you the forest where I'm headed. You want to put all of these things into this equation and say, okay, for example, this much of salary has to do with your sex. This much of it, this part of it has to do with your race. This much of it has to do with how many years of experience you have at work. And this much of it has to do with years of education you have. So you want to partition out why salaries are different. How much is the contribution of sex if we remove all other things out of it? How much is the influence of education if we remove or control for all other things? That is the pure impact of years of education. That's regression that I want to talk about. And you can imagine how important it is. No one ever publishes an article in a review journal doing t-test or ANOVA. Don't bother yourself. Do not even, don't waste your time to send it for publication. You do regression. And as you can imagine, it is such a broad topic that if you're going to take a, let's say, graduate course in statistics after this one, it's going to be all about regression. Then you get to, let's say, PhD working on statistics, it's all regression. So regression is the first really serious statistics. And it can take many forms, it can become complicated. So I want to basically teach you the basics of what regression is. Actually, I'm going to, since I have made notes for you, I don't want you to take notes, I have taken notes for you in here. Well, yeah, you can take notes if you want to. But I sat down, I prepared a lot of examples, and I wrote the conclusions of every term that is in there. So hopefully that helps. Doing it on SPSS is not a big deal. It is a simple thing to do, at least at the level that we're going to learn tonight. So sit down, relax, and be happy that we're getting into something very important. By far, much more important than everything we have learned so far. But to start with, I want to go over something called correlation. Correlation is a statistical term for relationship. And we have used that term constantly, all of us. Is there a relationship between the number of, let's say, courses you take and the amount of money you dish out for tuition? Is there a relationship between temperature outside and sales of coffee, for example? Or is there a relationship between the number of hours you spend studying and your grade? These are all correlations. There are different types of correlations. Actually, that chi-square test for independence, when you have two categorical variables, that's also a correlation. Remember that? Is there a relationship between gender and preference for software? There are two columns of data. One was Coke, Pepsi, Dr. Pepper, 7-Up, and so forth. One was, let's say, male, female, or black, white, Hispanic, and so forth. This is chi-square test for independence, correct? You are trying to find relationship between two categorical variables. This is chi-square for independence. Now, the type of correlation that I want to cover, which leads us to regression, is Pearson correlation. And Pearson correlation is actually, let me pass on this so you can. Pearson correlation that I want to cover is a type of correlation.
Oh, I have it.
Yes, that's it. It's a type of correlation that measures relationship between two continuous variables, not two categorical variables like that, but two continuous variables. Like what? Is there a relationship between, let's say, salary of people and years of education of people? Both variables are continuous variables. They are not categorical variables. So this is a Pearson correlation. So, and that's the one that I am interested in probably. That it looks like this. You have two variables. Let's say dollar amount of salary and let's say years of education. Here is 9,588, and then here 12 years of education. 6,080 decades and 16 years of education. Can you see the difference between this type of correlation and the other type of correlation? This is chi-square, both of them are categorical, whereas this one is, both of them are, let's say, ratio or interval level of measurement. So, if you have two variables that they are continuous variable, ratio or interval, then you can go to SPSS, go to analyze, correlate, and then bang, it tells you how strong this relationship is. And then when you run Pearson correlation, which again, you never do that by hand, the math of it is set in such a way that you get a number that is between 0 and absolute 1. Let's say the plus or minus. I'll talk about the plus minus in just a second. So if you get a correlation of 0, that means there's absolutely no relationship between the two variables. Imagine, is there a relationship between your hat size? Let's say, is there a relationship between the last 2 digits of your cell number and your shoe size? If you pick up 500 people and record the last 2 digits of their cell number and their shoe size, 500 people, and run a correlation, it's nothing, there is no relationship between shoe size and your cell number. You will probably get something close to 0. 0 means no relationship. Or if you're close to 0, that means that no relationship. 1 means whether positive or negative. It means perfect correlation. Is there a relationship between your tuition you pay and the number of courses you take? Yeah, perfect relationship. The more courses you take, the more you have to pay. Is there a relationship? Yes.
Will it always be either 0 or 1, or would it
No,
be like 1.4?
it would be somewhere in between.
Never over? Or
No.
never under?
That is what I wanted to actually bring to your attention, that the math of it is set up in such a way that it will be always between 0 and 1. It can never, write that down. Pearson correlation can never exceed 1. So on the, and I have already made that trick once on your test, remember?
Yes.
So I may make the same trick if I say that a researcher has done a test and got a Pearson correlation of 3.86. The right answer to those multiple choice questions that this is wrong, it cannot be. So 1 is perfect correlation and it cannot exceed 1. But the reality is that you will get somewhere in between in here, a number that is in between. If it is closer to 1, that means a stronger relationship. If closer to 0, that means weaker relationship.
Is there a level that you know where, like,
I know exactly what you want to say. But no, usually we use it for comparison.
You said closer to 1 or the closer?
If the closer you are to 1, the stronger the relationship. Closer to 0, lack of relationship.
So there's no deviation that we would say, like, if it's
You mean
0.75.
the cutoff point below that? No.
That's our say though, so we can't get a special one.
Yeah. It is only a, you look at it, it's good for comparison. And let me finish, and then, this is a legitimate question, by the way. Very legitimate question. But let me finish it, and then you get a feel for it. Go ahead, Morgan. Did you?
Was her question like, how do we tell when it's, if it's, because I asked you what the cutoff was, how close to 0 if it's, I think you're right.
Yeah. How much is large, how much is
Yeah.
small? That is what you want to ask. Let me finish, and then probably you will get. This is a good question, actually.
How
But,
close is too close to 0 for it not to count?
yeah, if it is close to, well, there is something else that after I finish it, then you get a feel for it. So this is the method that is set up in such a way that you get a feel for it. If you're closer to here, stronger, closer to here, weaker. It can never get outside of this boundary. There's one other thing that you want to know, and that is the sign of the correlation you get. That is, if you get a positive number, let's say if you get positive 0.80, for example. When you get a positive correlation, that means that both variables move in the same direction. When one goes up, the other one goes up. When one goes down, the other one goes up. This is called positive correlation. That means both variables move in the same direction. If one goes down, the other one also goes down. A negative correlation means that these two variables go in opposite directions. As one goes up, the other one goes down. Let me give you an example, a couple of examples. Is there a relationship between temperature and, let's say, sales of ice cream in, let's say, one of these ice cream places? Is it true that as temperature goes up, they sell more ice cream? Yeah, it's a positive correlation because the warmer it gets, as temperature goes up, sales of ice cream, for example, goes up in the city. As temperature goes down, the colder it gets, sales of ice cream goes down. So this is a positive relationship. A negative correlation would be when one goes up, it pushes the other one goes down. Is there a relationship between sales of coffee and temperature? Look at this way. As the temperature goes up, the hotter it gets, sales of coffee probably in city goes down. And vice versa. As temperature goes down, it gets colder. As temperature goes down, sales of coffee goes up. So you can see that relationship between sales of coffee and temperature is negative. So the sign, yes.
So what about if the temperature goes?
So when you get a number, the absolute number in here, whether positive or negative, doesn't matter. It shows how strong the relationship is. But the sign has to do with the direction of relationship. So if you get a positive 80, 0.80 or negative 0.80, they have the same strength. Is that this one a positive relationship, this is a negative relationship. So a very simple concept to understand, and of course computer will do that. Another thing that you want to know is that that's why you do not do these things by hand, because even doing this, it is complicated to do by hand. I think your textbook gets into the mathematics of it. I have never done that in real life. I used to teach students how to do it by hand, then I realized that I have never done it in real life. One other thing that you want to know, and that's why you do not do it by hand, is that, let's say you pick up 500 people, for example. Ask them, how many years of education do you have, and what is your monthly salary, for example. So 500 people, I ask them these two questions. Let's say on SPSS I run a correlation, and let's say that it comes out like this. What that means is that relationship between education, years of education, and salaries, it's closer to 1. You can say it's a strong relationship, more or less. And it's positive. That means that as years of education goes up, salary goes up. And as years of education goes down, your salary goes down. It's positive. Not only you want to know this number, but computer automatically will run a separate test, a test of significance for you. And that may get to the questions that you guys are asking. It runs a test of significance for you and tells you whether this number that you got you just got it by chance, or it is real. So that's why you don't want to do it by hand, because that even running a test of significance is another hassle. So if you get 0.80 and it is significant, it means that, yeah, there is a real relationship between education and salary. And it is relatively strong.
And SPSS will tell us.
And SPSS will give it to you. And it's positive relationship. As one goes up, the other one goes up, or vice versa. As one goes down, the other one goes
And it
down.
will give you that too.
Yeah, it'll give you the sign, it gives you the absolute amount, which is, it falls on the absolute number, between 0 and 1, and gives you the sign, which shows the direction of relationship.
I'm sorry, you were saying like 0.5 and above.
No, don't think of that. If you get 0.40, if it is not significant, that means this is garbage. There is no relationship. It didn't come as significant. But if it did come significant, you said, okay, there is some relationship between the two.
So the number doesn't matter unless it's in.
Yeah.
So that little asterisk is significant.
No, well, yeah, I put this, I
Oh.
meant that this
Well, I
is.
saw it on the chart.
Yeah,
so
I'll
I
explain
okay.
for you why you put asterisks. I put asterisks to indicate that it is significant. If I do not put asterisk, I mean it's not significant. So anyway, this is correlation. And there are a couple of other things that I need to mention is that, and you, most probably you have heard this many times on radio, TV, here and there, and that's that correlation is not causation. If there is if you find this number and it is significant, it does not necessarily mean that one is causing the other. Causation should come out of your own prior knowledge. Does it make sense? Or does it doesn't make sense that no, really doesn't make sense for education having to do with that. You need to have some prior knowledge to do that. Second, if you know there is a causal relationship, this doesn't tell you. Let's say that we know that education has to do with salary. Or we know that, for example, temperature, that's a better example. We know that temperature has to do with sales of ice cream, for example. The higher temperature, the more sales of ice cream. Yeah, it makes sense. But this correlation that you get in here will not tell you the direction of the relationship. Is it that the temperature causes more ice cream to be sold in the city, or is it that the sales of ice cream in the city causes the city to get colder? It doesn't tell you that. You need to have some prior knowledge that it doesn't make sense. Sales of ice cream making the city colder, no, it doesn't make sense. So really, two things you need to, when you get this number, two things you need to consider. One is that, does it make sense? Is there a real relationship? I'll tell you a couple of examples of why there are sometimes spurious relationships. I'll give you an example. Second is that if you know that, yeah, it makes sense, there might be causal relationship, then again, you have to think which way is the direction of the causal relationship. So my point is this. This doesn't tell you anything about causation. Causation should come out of your prior knowledge. That's what I'm trying to say. You may run into a situation that even if you get positive, high, not is a very large, closer to 1, very significant. Still you need to think about it to see if there's causation or not. Let's say I want to know, this is my favorite example. Is there a relationship between corruption in a city and then level of religiosity of people? Is it that the more religious people are, less corruption and this kind of thing? Imagine I want to test that. I go and pick up 500 cities in US. Here's San Marcos, Austin, Dallas, and so forth, 500 cities in here. I go, let's say, to FBI records and see what's the crime rate in San Marcos, for example, 40%. I'm making up a number. And how many places of worship exist in San Marcos? I am assuming I'm going to measure, let's say, level of religiosity of a city by how many places of worship they have. Obviously, if you do not have any place of worship, that means that those people are not religious. So let's say in San Marcos there are 64 places of worship. Mosques, synagogues, churches, temples, whatever. Then I have all these numbers in here. For every city I've collected two numbers. Crime rate, number of places of worship. I bet you, if you run a correlation in here, you get something very positive, and you get something, might get something like this. Almost one, a strong relationship as positive. The higher the number of places of worship in a city, the more corruption and crimes in the city. And less place of worship, less corruption. Does that make sense? Just doesn't make sense. Even though this number tells you there's a positive relationship, very strong, is significant. So you need to give it some thought. And of course the trick in here is that obviously the size of the city affects both of these two numbers going in the same direction. The larger the city is, the larger number you get in here, the larger the city, obviously crime rate is high, correct? So you can see that there is a hidden variable out there that moves these two numbers in the same direction. My point is this, that if you get a number, give it some thought to see whether it makes sense for causality or not. Yvette, go ahead, I'm sorry.
What if you pick cities with around the same population size?
I'm sorry?
If you pick cities that have the same population size?
Sure, okay,
Would you
yeah.
still find the same relationship?
No, if they're the same size, no, you will not get that. Here, my trick was, obviously I picked out a small city in here, and a large city in here. That was the trick I made in here. But give it some thought. The issue of causality has nothing to do with correlation. Correlation would just give you, of these numbers that you gave me, yes, there is a relationship in here, it's a strong and it's a positive. But causation is something that should come out of your own prior knowledge. I'm sorry.
Is it like that example with the crime rates and the ice cream in the summer?
Yes.
Said yeah, crime rate and what?
Like,
Ice cream?
you know that example, it's like really common that people use, that it's like there's more crime in the summer, but at the same time there's also more ice cream sales, so like ice cream causes crime.
Yeah, that's right. That's another a good one.
Yeah.
Is there a relationship between the number of donkeys in a city and the number of professors in the city? Obviously, you will find a positive, strong number. Excuse me, negative number. Fewer donkeys, more professors in the city. Which makes sense, huh? Higher donkeys, less professors. Think about it. It makes sense. Because in small towns, villages, you have more donkeys. Obviously, those obscure places, you don't have much professors.
Is there ever a case where both could be used? Like where it could go either way, like the salary goes up when the years of education go up, or the years of education go up when the years of salary, like, to switch it, if that makes any sense. Was there ever a case where you could make it both?
I'm not sure which is.
Or would
Here
that be
is-
the same direction?
If it comes positive, it means both move in the same direction. That means if this one goes up, this one goes up. If this one goes down, this one will go down.
But as far as like the causation, like creating the
The
causation.
causation has nothing to do with this. You need to think about it. Yeah, it all comes from here. Yeah, like in this one, yeah, it makes sense. If you do not have a high school diploma, you probably do not make a lot of money, generally speaking. Let me see. Oh, there's one other thing, the final thing. I need to tell you. Let's forget about the issue of causation. So we have, let's say, two variables. The temperature, we're measuring the temperature of the city. Let's say one of these ice cream places, the manager has gone to the last year, records of last year, last 365 days. For every day, he has recorded two things. What was the temperature on January 1st? How much dollar amount, for example, ice cream did I sell? How about January 2nd? What was the temperature? What was the sales of ice cream? January 3rd, January 4th, and then let's say for 1 year, he has the data. Two columns, continuous data. Remember, we're not dealing with categorical data. Runs a regression and, not regression, excuse me, correlation, Pearson correlation. And let's say that gets this number. Positive number, 80%, excuse me, by the way, this is not a percent. It is from 1 to 0 to 1. Do not look at it as a percent. This is not a percent. You get 0.80 relationship between temperature and sales of ice cream. It is significant. I'll put this asterisk to remind you it's significant. Now, there are times that you say, oh, okay, yeah, it makes sense. Temperature strongly affects sales of ice cream. Sales of ice cream has a lot to do with the temperature. Remember, this is close to 1. What happens if you want to know how much of the sales of ice cream has to do with temperature, how much of it has to do with all other things? Obviously, sales of ice cream has to do with a lot of things, correct? Temperature is one of them. How many kids are in town? The more kids, obviously, the more ice cream. So, the income per capita of people, the wealthier the people are, the more ice cream probably they eat. A lot of things contribute to ice cream. You want to know what is the contribution of temperature on ice cream? How much of ice cream is caused by temperature? If that is the question you want to know, all you need to do is square this number. So if your R is 0.80, square it, 0.64, very important number. This is a percentage. This is not a percentage. It's like, this one is like that when you're downloading the bar that it shows you how much you're downloading. It doesn't matter what the length of the bar is, huh? That's not a good analogy. This is just tells you from 0 to 1, you're closer to here or closer to here. This is the number.
What does R stand for regression?
R squared, which is called coefficient of determination. Nobody uses that term anymore. We call it R squared. That's better known. R squared is very important and see, tells you a lot of things. 64% of the sales of ice cream has to do with the temperature. 36% of the reason that sales of ice cream goes up and down has to do with all other things, number of kids, income per capita, location of the, probably the ice cream place, whatever you can think of. 36% of the sales of ice cream has to do with all other things. 64% of the sales of ice cream has to do with temperature.
And R squared is always a percentage?
R squared is always a percentage. Let me warm up the computer while I am waiting for this to come up. It is extremely simple. It is extremely simple to do it on computer. Probably the easiest everything we have learned so far. And it's not a difficult concept to understand. Correlation, Pearson correlation, it basically gives you two things. strength of relationship between two continuous variables, and the direction of the relationship. That's all it gives you. It has nothing to do with causality. Another thing you need to know is that if you square that number, which is called coefficient determination again, people do not use that, and we call it R squared. That R squared is a percentage. It gives you what percentage of variation in one variable, let's say sales of ice cream. What percentage of variation in sales of ice cream has to do with the other variable, in this case, temperature.
You could do it with both variables though. You could square temperature.
No, you get only one number. Relationship between temperature and ice cream is this number,
Oh.
correct? There's only, you get one number.
And the distance between that relationship is squared. Or
If you square this number,
you get the distance.
you get a percentage has a special meaning. The meaning is that how much of this variation in this variable is influenced by the other variable. How much of sales of ice cream has to do with temperature.
So the other percentage, the other part would be the remaining factors. We wouldn't say like one specific one, we just put the other percentage left over from that would be.
Left over has to do with all other things that we do not know what they are.
So it would all be unknown.
Yeah, it's unknown, and that's what I want to deal with in a few minutes when we get to regression. Because you want to know those two also, huh? You want to know that, we know that this much of the sales of ice cream has to do with temperature. How much what's the contribution of the number of kids in town? What's the contribution of income per capita of town? What's the contribution of, many other location? We want to also, that 36% that is left, we want to find the contribution of each one of them.
How is that even possible if there's unlimited, I feel like there could be unlimited factors involved, right?
Yeah, very good. I'll get to that. A lot of things you do not know. So when you run, we're getting way ahead. We're getting into regression now. Then those variables that you know, for example, number of kids, this, and then you put them in regression, it gives you the contribution of those things that you have determined. And then it gives you another piece, a small amount, so that this much you have not considered. Imagine if there's 10% has to do with the number of kids and 5% has to do, with location. The remaining is 13% some other things that we do not know. But correlation, all I want to tell you is that Pearson correlation is a statistical procedure that measures strength of relationship between two continuous variables. It gives you a number, and on purpose they have set up the map of it in such a way that you get a number between 0 and 1, and the closer to 0, that means weaker relationship, or 0 means absolutely no relationship. Closer to 1, that is a stronger relationship. 1 is perfect relationship. And this is, don't read it as a percentage. Just closer to this end or closer to the other.
You said don't read this?
No, this one don't read it as a percent. This one read it as a percentage.
Yeah, because 1 times 1 would be 100. If we had 1, right? it'd be 100%.
In here?
Yeah, yeah.
Okay. How do we do it on computer? Now, let me see. Can I find relationship between age and salary? Can I do a Pearson correlation?
Yes.
Yes, both of them are valid. How about age and years of education? Can I run a Pearson correlation? Yeah, both of them. How about age and gender? Can I do that? No, because this one is categorical. Both of them should. How about gender and race? How about, age and job satisfaction? Yes, because this is an interval level of measurement. I'm measuring satisfaction on a scale of 1 to 7. Remember
Says
these
one.
Likert scales are interval level. It's okay, you can
So we
consider.
would have to change job satisfaction to 1, 2, 3, 4, 5, 6.
Yeah, it is already done. I have already coded it as 1, 2, 3,
So
7.
you're saying when you do the comparison test, they both have to be interval categories?
Both of them have to be either ratio or interval.
Ratio or
Either,
interval, okay.
yeah. Continuous variables.
Okay.
Not, or put it this way, it cannot be nominal or ordinal, it cannot be categorical, none of them can be categorical. So I can use job satisfaction, I can use education, I can use salary, I can use age. But these two variables are categorical. Yeah, I've coded them, but they are categorical. So if I want to run a Pearson correlation, I go to analyze. Can you imagine where I need to go? Matthew, can you imagine where I need to go to do correlation? Possibly, what's the best candidate? Perhaps correlate, if I want to run correlation between two variables, do you know where I need to go?
The first one by variable.
By variable, okay. And if I want to do Pearson correlation, I suppose that's it. All you need to do is move your variables from left to right, and that's it, done. But here's the good thing. Most probably you want to run bunch of correlations. You don't want to do bunch of separate correlation. In one shot, you can run bunch of correlations. For example, I want to know correlation between age and salary, age and education, age and job satisfaction, salary and education, salary and job satisfaction. Move all of the variables that you're interested from left to right, one shot. No, I didn't bring gender and right and race, correct? Because these are categorical. So you bring it from left to right and make sure that Pearson is on in here. Click OK, voila, here is your Pearson correlation. It is cluttered. The way that it comes out, it is very cluttered. Let me get my. So if you look at this, you see that the rows, age, salary, education, and job satisfaction is the same as column, age, salary, education. So diagonally is basically a relationship between a variable and itself. Wow, this is perfect. No?
What do you mean diagonally?
Then from here.
Oh, okay.
It's like, do you remember that multiplication table that you used when you were in elementary school?
Yeah.
Here 1, 2, 3, 4, 5, 9, and then 1, 2, 3. So if you notice that this diagonally, if you look at it, the upper triangle is a mirror image of this lower triangle, correct? Relationship between age and education is right here. Now, relationship between education and, let's say, excuse me, this is age and education in here, and then you can find it in here too. Age and education right here.
How's that diagonal?
How can you tell that's age and education just because it's a matching number, but what if the number just appears twice? Wouldn't that be education? Oh, never mind, I'm an idiot, education and age, it's just.
Age and education, relationship between age and education, from 0 to 1, you got 0.32, correct? You're around here.
Yeah, I see it.
And came out significant. So there is some relationship between your age and education. And what I'm saying is that now age and education in here. So if you look at this diagonal 1, 1, 1, 1, that means relationship between a variable and itself. Salary and salary. Obviously, 1. Perfect. And this upper triangle is mirror image of this lower
Why
triangle.
does it repeat so many, like,